astrobiology. Our two speakers are, first up, Dr. Ariel Anbar. Did I get it right? I've been practicing. He is the director of the ASU Astrobiology program. He is researchers in Dr. Anbar's group use chemical concepts and approaches to study geological, chemical, and biological processes that shape the Earth's surface environment and how they have changed through time. Our second speaker up is Dr. Stephen Desch. Did I get that right? Desch? Close, pretty close. He's a theoretical astrophysicist here at ASU. Stephen Desch is a theoretical astrophysicist who models the formation of solar systems and planetary processes. His modeling draws on his expertise in the magnetohydrodynamics.
Yeah. I don't know what any of that means.
I don't know either.
Okay.
Radiative transfer, dust microphysics, meteorics, and other astrophysics, as well as numerical computing. All right, everybody.
Thanks. Is this, can you guys hear me? Is this working? It's not that big a room, actually. Okay, so what we're going to do here, we're going to do a little tag team. I'm going to give an overview of astrobiology, a little bit of philosophy and vision. Rick is a really hard act to follow, but I'll do what little I can. And then, so that'll be about 20 minutes, I hope, and then that'll hopefully set up Steve nicely for, I think, a more technical talk about exoplanets and what planets outside of our solar system might be like. So what I want to do here is give you sort of an overview. It's kind of a personal overview of what astrobiology is all about. And we'll do this a little bit by teeing off of some recent news. About a month ago, there was a lot of news about Mars, about the search for life on Mars. As you guys know, the Curiosity rover is roving around Mars right now, doing, among other things, various analyses that are designed to look for evidence of past life as well as habitability on the surface of Mars. And one of the things that it was designed to do was to check out, to try to verify reports from ground-based observations that there might be methane in the Martian atmosphere. Methane is very exciting to astrobiologists because one of the ways that you can produce methane is by biology. And if there was the amount of methane that had been reported in the Martian atmosphere and as variable in its amount, its abundance as had been reported, it would be hard to get away from the idea of biological production, or at least maybe not hard to get away, but it would be very compelling evidence to a lot of people that there might be life on Mars today, microbial life producing methane. So Curiosity looked for methane in the Martian atmosphere, and finally they concluded and put out a paper about a month ago saying not a whiff of life on Mars. They found no methane or nothing anywhere approaching the levels that had been previously reported. And if you read the press accounts of this, they were reported as a great disappointment. This finding will disappoint many people. This kind of quote appeared over and over in the news accounts. And you can understand that. I mean, it would be really tremendously exciting if we found life off our world. That is one of the things that the excitement of that is one of the things that motivates us in this search for life beyond Earth. It would be particularly exciting if we found it next door on Mars. But what I want to try to get across to you guys today is a view that's maybe a little controversial, maybe it's not quite the conventional wisdom, which is that you shouldn't be disappointed, actually, if we don't find life elsewhere. Even if we search and search and search and search and find out that we are actually completely alone, that's not necessarily disappointing. It's just it's not what we expect. But it actually, in some ways, it's at least as profound and maybe more profound. Rick actually touched on this in his talk, and I'm going to elaborate on that a little bit. So, first thing to realize of why I'm saying this is because the search for life beyond Earth is not a search for Holy Grail. It's not a religious quest. It's not as though if we find life out there, we have fulfillment. And if we don't find it, we've failed in some grand quest. Right? But too often, this is the way people think about it, especially the general public, but even lots of scientists think about it this way. We are engaged in some grand quest that somehow will bring us some great emotional fulfillment if we succeed. And by inference, if we don't find life elsewhere, that must mean it's a failure somehow, and it's a sad thing. I mean, I like Star Wars and Star Trek. I like the idea of a universe teeming with all sorts of intelligent civilizations, so I can understand why it's, in a sense, a sad thing. But in a bigger picture, I don't know that's necessarily a sad thing. It is a thing. It is a reality that we would discover, which is profoundly important. Are we alone? There's two possibilities. It's either yes or no, and what my thesis to you today, what I want you to walk away from today thinking about, realizing, pondering, is that either answer is profound. Either answer is profound. It's not that we'll be happy if we find it and sad if we don't. Either answer is profoundly important. And I want to put this in a historical context for you a little bit so you understand where I'm coming from. So a few hundred years ago, we had this notion, the Ptolemaic conception of the universe, that the sun was at the center of all creation. I'm sorry, that the earth was the center of all creation. Get it backwards. And, you know, everything, including the sun and the moon and the stars, everything revolved around the earth. We were very, very special, privileged observers of the universe because the universe revolved around us. And as you guys all know, I presume, a bit later on, and again, Rick alluded to this, Copernicus came along, 16th century, and devised a very different conception of the universe. This wasn't just out of whole cloth. He was trying to, the Ptolemaic system, the more the data built up, the Ptolemaic system was just harder and harder to reconcile with the data. It could be done, but you ended up with kind of hideously complex scenarios to make it all work. So Copernicus came up with a concept that was, at the initial version of it, was actually just a little bit simpler, but it was simpler. And later on, you know, it took hold because it's much simpler, as it turns out, the more data you have. And this was a conception that the sun is at the center and the earth revolves around the sun, and all the planets in the solar system revolve around the sun. And so the earth was demoted, right? We were demoted from this position of special, unique location in the cosmos to, oh, we're kind of a little bit off to the side. And as we learned more and more, as astronomy and physics became more sophisticated, we became better observers, we learned that not only is the Earth not at the center of the solar system, but the solar system is nothing special either. We're off here in the suburbs of our galaxy. And our galaxy isn't anything particularly special in the sense of being privileged location in the cosmos. Our galaxy is one of 100 billion galaxies, give or take, in the observable universe. Right? So the march of scientific progress has been to teach us that we are not privileged observers. Right? And all of modern science really is founded on this. And we give this in philosophy of science and philosophy in general, we give this a term, the principle of mediocrity, which does not mean, it's not a principle that says you guys shall be C students and that you shall party like it sounds like you guys did last night all the time. It's an idea that says that no observer in the universe is privileged over any other observer. The physical laws that govern physics and chemistry, and we presume biology, are universal and will apply everywhere in exactly the same way. And, you know, socially we kind of adopt this too. We have this principle, right, that we've adopted in democratic societies that none of us are privileged relative to each other, right? I don't have any special rights compared to you, right? It's very interesting to think about. We don't usually talk about it this way in standard science courses and thinking about it, but there are incredible cultural connections between what scientists learn and what societies end up doing. And I don't think it's a coincidence that a couple hundred years after Copernicus, you go into the Constitution of the United States and you see a phrase like this: we hold these truths to be self-evident that all men, all people, are created equal. Right? I don't think it's an accident that the political philosophers a couple hundred years after Copernicus adopted this notion that no individual is privileged. It's a very logical inference, right? Very logical follow-on from the notion that physics was teaching us that there's no privileged, that we aren't privileged observers in the universe, right? There's a very close tie there. So these scientific observations that we make that teach us about our place in the universe are not just interesting curiosities. They're not things that, you know, you talk to somebody over a beer in a bar and they say, oh, that's nice, and then they go on their merry way. They actually penetrate and influence the way we interact with each other as human beings over generations, as these ideas seep in. These kind of philosophical constructs seep in and affect the way we think about how we should organize ourselves and how we should relate to each other. I think that's really true. So physics has taught us this. Physics and astronomy has taught us this. And we assume that since biology is basically, you know, can be reduced to chemistry, and chemistry can be reduced to physics, we assume that this principle of mediocrity also holds in biology. We assume that if atoms can come together to make molecules, molecules come together to make materials, materials can come together to make planets, planets come together to make solar systems. We assume that because that happens here, it'll happen elsewhere, and we're testing that hypothesis right now. And we assume, as we continue on from that some of those atoms and molecules can get together to make organic compounds, and those organic compounds can self-organize into complex emergent systems that we call life. And we assume that since that happened here, that can happen anywhere. So we assume that, we're not some unusual tall poppy in a field of, or a singular poppy. We assume that there's poppies everywhere. But that's an assumption that needs to be tested, like any other assumption in science. And you can make the case, and it's usually made by creationists, which is why we as scientists don't talk about it, but it is actually a very real thing that scientists, in the fringes, or not the fringes, but quietly do talk about, and it's a very important thing. Biology is hideously complex. So this is a metabolic map put out by Roche, a pharmaceutical company, of the human body. And all these lines are connecting different molecules, the reaction pathways that your body has evolved over billions of years. And I'm not here to say that God intervened to make this happen. That's not at all what I'm saying. Don't get me wrong. But this is hideously complex. And it stems from an event, the origin of life, that is, hideously complex. It stems from an event, origin of life, that is not understood at all. We understand, we think we know the contours of what's important, what the boundary conditions are for the origin of life from thinking about the Earth, but we don't know how it happens. We don't know if it's an easy thing to happen or a very improbable thing to happen. We tend to make a statistical argument. When we have conversation about this, we make the statistical argument. We say, look, there's 10 to the 22 stars in the universe. 100 billion stars per galaxy, 100 billion galaxies in the universe. 10 to the 22 stars. And all that immensity, it's improbable that we're alone. What are the odds? Well, yeah, it does seem improbable when you think about it that way. On the other hand, when you beam around in Star Trek, what's the transporter doing? The atoms in the body, there's 10 to the 27th atoms in the body. The human body is organized, working in a very complex dance and interaction that had to evolve through a whole lot of chance events to get to here. Right? There's a million more atoms in the body than there are stars in the universe in a single human body. And the point here is biology is intensely complex, and we do not really know. We do not really know, when you think about it, what the odds are. So we can sit back and say, there's all these stars, what are the odds that there isn't life elsewhere? And the answer to that, if you really think about it, is, well, we don't really know the odds well. Maybe life is a once in 100 billion in 100 billion event, and we are the one place where it happened. We have this bias from physics and astronomy, principle of mediocrity, that, well, that can't be true. There's got to be life elsewhere. There's planets elsewhere. There's got to be life elsewhere. But we don't know. So what we are doing in astrobiology is not a religious quest. What we are doing is we are testing a hypothesis. We are testing whether or not this principle of mediocrity, which we know works in physics and chemistry, does it really hold in biology? Are we typical or are we atypical? Right? What are the odds? We don't really know. We want to know that. That's why, in my mind, that's why we're searching out there. We want to understand this question. We want to tackle this question scientifically, not just by our intuition that, oh, well, it's improbable. Well, that's nice. We need to know the odds, and the best way to know it, I think, we could get into, doing lab experiments on origin of life versus looking out there. I mean, I would say we're going to make progress faster by searching out there than we are by doing lab experiments. That's a whole other conversation. Both need to be done, but I think, one finding of life elsewhere that's a de novo origin of life would answer a question that it will likely take centuries to figure out in the lab. So let's talk a little bit about the bigger implications of that, just very briefly. So let's say it turns out that we are alone. Rick touched on this too. Let's say it turns out that the origin of life is a very low probability event. Or maybe the origin of life is not that low probability, but the origin of intelligent life and sentience is a very low probability event, the so-called rare earth hypothesis. That microbial life might be common, but that the confluence of events that lead to evolution of thinking beings like us is a whole bunch of contingencies that are incredibly unlikely. Well, if that's true, then the Earth is a very unique place. And it's hard for me to imagine that that would not have all sorts of very interesting ramifications for societies and how we think about things. Certainly from the standpoint of thinking about how we should take care of this place, the arguments would become much more heightened. If this is the only place in the universe that has life or that has intelligent life, then what we do with this place, the stakes literally become astronomical. Right? If, as Rick put it, if we are the universe figuring itself out and we manage to wipe ourselves out, we've killed the universe. I mean, this is the biggest stakes you could ask for. Right? It's not just about do our kids live in a cleaner place or a dirtier place. it's hard for me to imagine that would not have very profound ramifications for how we view our planet and what we should do with it, how we should treat it. And then to leave you with one other thought about related to all this, because I've mentioned the science and religion, I've touched on the science and religion interplay a little bit. Let's think about this a little more deeply. You know, I have a lot of friends who are religious folks, and we argue, you know, about evolution and all this kind of stuff. My brother is a physician who's by no means a creationist, but he thinks somehow God intervenes in the world to do things. So we have lots of debates about this sort of stuff. And when you get past the, you know, belief in miracles, or is the Earth 6,000 years old, and all this kind of stuff, you know, why is there this dichotomy? Why is there this split between science and religion? Why do the religious people feel that science is somehow against them? And we do need to think that way, because the reality is there's more religious people in the world than there are science people in the world. So if we want to convince them, we want to understand that mentality, that worldview. What it often comes down to, when you strip it away, is this notion that folks have that science somehow makes humanity and human beings seem less special. That it takes away meaning somehow as we learn more and more about the universe. And I think very much that this goes back to Copernicus and this principle of mediocrity, that the march of science has been, and I realize what I'm saying here is controversial, and we can talk about it a little bit later, but I think the march of science has been largely perceived as, because it in many ways has been, this march to say, you know, nobody has privilege, nobody is special, nobody is unique in the universe. That's the way it's perceived. And it's a misstatement of reality, but it is the way it's perceived, certainly by religious people. I have a feeling that if it turned out that we are alone, and we started to think that the Earth is, or at least very, very unusual, if we started to think that the Earth is a very unusual place, maybe one of a very small number of places in the universe that have life, maybe the only place that in the universe has life, I suspect the conversation between science and religion would change quite a bit. You know, if scientists start proving that this is a very special and unique place, and that becomes a lot of the language that we use, because that's what we're finding in our science, the conversation between science and religion will evolve and change. And we may look back 500 years from now at the past 500 years as an interesting epoch where these two ways of trying to know the universe split apart, but then they sort of came back together when science kind of came around to a view that is not that dissimilar from that of many religions, that the Earth is a very special and unique place and all that kind of stuff. I can imagine 1,000 years from now, we look back at this period of conflict as sort of this teenage conflict, like a teenage kid fighting against his parent or something like that. And then as both sides kind of mature a little bit, they get back together and realize, well, you know, there's different ways of knowing, and that's okay, and we can live together, because we more or less are kind of saying the same thing, that we're special, and we need to be thinking hard about how we behave towards each other and all that sort of stuff. So this astrobiology business is not esoteric. It's not just curiosity driven. It is at the core of our understanding it cuts to the core of understanding of who we are and our place in the universe, which is something that is profoundly important, not just to science-oriented folks. Finally, I just want to say a few words to help set up Steve here about, okay, so where and how will we search? And most of you know all of this or some of this, but maybe not all of it. Maybe not all of it. So obviously we're searching on Mars, and despite all the effort we put into Mars, really the search there has only just begun. We know that Mars was habitable. This is something that we argued about 40 years ago, but now there's not much argument that Mars at least was a place where life could have existed, at least microbial life. And even today there are environments on Mars, probably in the subsurface, where Earth life could probably survive, microbial life. Mars, even today, is arguably a habitable environment. So that's why all the attention, right? And it's not just because science fiction authors, it's not just because, 100 years ago people thought they saw canals, which didn't really exist. There really is good scientific reason to be obsessed with Mars in terms of search for life. The other candidate that gets a lot of attention in the solar system is Europa. And not just because Arthur C. Clarke was very prescient about Europa, for those of you who are aware of what he wrote about it, but because we're pretty convinced there's a subsurface ocean on Europa. It's very hard to get to. There's kilometers of ice between that ocean and the surface, and getting through that is a daunting challenge that will not be mastered anytime in the near future, but it's a challenge that motivates a lot of thinking and eventually will motivate some very fascinating exploration. I want to put in a plug, though, for one other world in our solar system that you might not have thought about, and this is Enceladus. It's a tiny little moon of Saturn. It's a tiny little moon of Saturn that is spewing. This is an artist's impression. It's not quite this impressive in real imagery, although it might be this impressive in person. This is an artist's impression of the jets of water that are spewing from the interior of Enceladus. So Enceladus not only has some large subsurface body of water, an ocean of sorts, it appears. That's the best interpretation. But it is spewing that material into space. Unlike Europa, where it's locked up beneath kilometers of ice, in the case of Enceladus, it's actually saying, come get me. Take a look. See what's in here. And there are those of us who are actually actively trying to figure out a scheme to send a mission to fly through these plumes and bring material back to the Earth. And it's not just that there's water there and energy. You need energy and water for life. Those are two prerequisites for life as we know it anyway. You also need critical elements that are important for life as we know it. You need nitrogen, phosphorus, things like that. We know from the direct detection from the Cassini mission that there is nitrogen in the plumes of Enceladus. And we can make a very strong case there's probably phosphorus there because there's a rocky interior to this body. And then finally, what you would like to have real confidence that this is an interesting place to search for life is presence of organic molecules. And one of the really exciting findings from the Cassini mission to Saturn in recent years is that there do seem to be large organic molecules in these plumes. So you've got water, you've got energy, you've got at least some of the bioessential elements, and you actually have some organic chemistry that's happened there. How far down the path towards life has it gotten? We don't know. If life is really easy, maybe it's there. If life is really low probability, then not. But either way, this would be a very interesting place to try to extend our knowledge. And it's reachable. It's doable. With technology we have now, we could do this mission of going through there, grabbing material, and bringing it back to Earth. It doesn't require grand technology development. It just requires will, just requires some money. And then finally, what's most exciting to a lot of us, and this will set up what Steve is going to talk to you about, are exoplanets, planets outside our solar system. When I was your age, which is a little longer ago than I would like it to be, this was fantasy. This was Star Trek stuff. It's not Star Trek stuff anymore. It's real science. So we now know of, for sure, well, for as sure as you get, almost 1,000 planets outside our solar system, with thousands of more that are candidates that are likely to be confirmed with further observation. And we've only searched a very tiny portion, actually. The search space is actually very tiny that we've been looking at. If you follow the news on this, then you saw that just last week there was a Kepler science conference. Kepler is the space telescope that is finding a lot of these planets now. It's the dominant way now that we're finding extrasolar planets. And one of the big splashy findings from this conference was an estimate that there are about that 1 in 5 sun-like stars has got an Earth-like planet in its habitable zone, which means the planet is not so close that it can't support liquid water at its surface and not so far that the liquid water would freeze. There's a lot of inference that goes into that statement, but that's the headline that came out of it, 1 in 5. And we could argue about that. Maybe it's actually 1 in 10. Maybe it's actually half. There's a lot of arguing going on about that particular number. But it's hard to get away from the fact that there are almost certainly lots of Earth-like planets, if we define Earth-like sort of broadly, capable of having a liquid ocean at its surface. There are probably lots of planets like that out there, if conditions are right. And so that sets up Steve, I think, because I believe what Steve is going to tell us about, unless he's radically changed his talk from last night, is he's going to talk to us in depth about one of these types of worlds. He's going to talk in depth about so-called water worlds, worlds that may be very much like Earth, but with a lot more water. What determines whether such planets can exist, and what might they be like? Are they good places to search or not? So Steve. You want that?
Yeah.
You want the, which mic do you want? You want this?
Alrighty. Oh, where's my talk? It's on the wrong screen. There we go.
You got it?
Yeah. Well, that's the wrong PowerPoint. Got 2 PowerPoints up.
Quick, go to your email.
I know. Hold on. Where'd my go? Here it is. It's over here. It's off my screen. I need to get there. Something's happening. It's mirrored. Yeah.
Yeah, so just go on to this.
Right. Super. Thanks. Yeah, it's really shocking. When I was your age also, we did not know about any exoplanets. And so that's an incredible advance in our field. And I don't feel that old, so it's a really rapid advance, I'd have to say. It's incredible that we have 1,000 planets. There are philosophical ramifications of finding these planets, as Ariel alluded to. And there's much more practical ones. If you are wanting to explore the universe, then you're going to want to live somewhere. And in some ways, I view myself as a real estate appraiser. You know, what's out there, what's available, what's on the market, and what environments are good for life to live in. And that's the very first question you must ask. When you want to look for life in the universe, you've got to know, well, where's life going to live? It's going to live on a planet. And different planets are going to behave very differently chemically than our own planet. Perhaps they have different challenges. And before we can even start to think about how life might be detected on these planets, we have to think about what the planets look like. One of the big surprises in the last 2 decades is that planets out there appear to be, well, there's a diversity of planet types. They're not just like Earth. And there are apparently many planets that are Earth mass-ish, that exist near their stars at about the same distance the Earth orbits the Sun at, which is 1 AU, 1 astronomical unit. I'll use that a lot. So the distance from Earth to the Sun, 1 AU. And yet, these planets may be very different from the Earth in that they're totally covered with water. And this has been recognized as a planet type, and we may have even discovered some already. So we call these water worlds, and they've been speculated about for a decade or so. Earth-like planets, mass is comparable to Earth, but a substantial fraction of the mass being in water or perhaps ice. Now, the Earth is not a water world. I always joke, if you lived in Arizona, you would know this, that it's not a water world. But let me just go through some of the numbers here. When you look at the volume of all the oceans, water on Earth, and you look at the surface area of the Earth, you can figure out the average depth of the oceans is about 3 kilometers. And the mass is about 1.5 times 10 to the 21 kilograms. And when you divide that by the mass of the Earth, you find the Earth is 0.03% water. That's it, 0.03%. We tend to think of the Earth as a very wet planet, and most of the surface area is covered in water to depths deeper than we can stand in, but it is nevertheless a very dry planet. The water that's there doesn't really change the density of the Earth, which is mostly determined by the fact that it's got an iron-nickel core and silicate mantle. Its density is about 5.5 grams per cubic centimeter. And that little skin of water doesn't make a dent in that number. So the Earth is not very much water. But when you look at other things in our solar system, Pluto or other Kuiper Belt objects beyond Neptune, or just look at the asteroid Ceres, or the moons of the giant planets, most of these objects have water, ice to rock ratios that are in the range of about 0.5 to 1 or more for Saturn's moons even. So, you know, water and rock, just in the universe, we expect them to be equally abundant. When you look at the elements that are in the sun, you'd expect water and rock to be equally abundant. When you look at these outer satellites and other objects in the solar system, they're equally abundant. And yet the Earth is very, very dry. Earth does not have that sort of water content. So when you think of water worlds, you know, the Earth is not a water world. And when you go through those numbers, you realize something like this could never happen. You know, the movie Waterworld really bugged me because they started off the movie, and before they even started the plot, they showed the little logo of the Earth, the universal logo, and then the ice caps melted, and then the Earth was covered in water. You know, there's no land anywhere. That could never happen because there's just not that much water. When you look at all the volume of ice that's on Antarctica, if you were to melt it all, you would increase the height of the oceans by 0.06 kilometers. And just for reference, Phoenix is currently 0.34 kilometers above the sea level. So, you know, you just couldn't do that. I put the price of Waterworld up there too because it came out at the same time that the Pathfinder rover went to Mars for less price. I would really much rather have a mission to Mars than another movie like that. So the Earth is not very covered with water, and I sort of draw this in PowerPoint. You can't get any finer than that. It would be a thinner skin than this. But given that a lot of other objects in our solar system have substantial water-to-rock fractions, you can imagine a water-to-rock fraction of 0.1. That wouldn't be so big. And then you'd have, this is more to scale, oceans that are completely covering the Earth to depths of 700 kilometers. Not 3 on average, but 700 kilometers deep. And if there was a water-to-rock ratio of 0.5, that would be much more typical for the outer solar system. Then we would have oceans that are 3,500 kilometers deep. We're talking a substantial fraction of the Earth's radius. And we recognize that if you have Earths with this sort of water-to-rock ratio, that's how deep the oceans are that we're talking about. Now, since this has been speculated about in the last decade, there's been some theories about how the planets will be put together. Some modeling back in 2004 showed that the bottom of that ocean would be so deep and under so much pressure that it could not exist as water. This is a phase diagram of water. You have pressure, which is a proxy for depth here, on this axis, and temperature on this axis. Green is liquid. That's the temperature range and the pressure range that can exist as liquid. And you need to be above 0 Celsius at sea level. Actually, if the pressure is higher, you can have water even at colder temperatures. All of our oceans sit around here in this little space, this little line. Once you start talking about oceans that are hundreds of kilometers deep, you eventually, for any reasonable variation of temperature with pressure, you run into this boundary up here where you have high pressure phases of ice, like ice 6 or ice 7. There's no way you can have an ocean that deep and have it be liquid all the way down. So the structure of the planet is probably more like this. You have a big rocky core, and then an ocean on top, but in between is this layer of ice that could be 100 kilometers thick. And this is going to be a structure that we would find on any planet. There's a water-rock ratio that is more typical of cosmochemical abundances and not like Earth. And this has been speculated about for about a decade now, and thanks to Kepler and other follow-up ground-based observations, we are now finding that such planets almost certainly exist. So one example is GJ1214b. GJ1214 is a nearby red dwarf star, only 42 light years away, and it has these sorts of stellar characteristics. It's about as old as the Sun, 6 billion years old. And it's tricky to get this information. If you want to know the mass and the radius of a planet that is orbiting a star, you can detect the planet through the wobble that it gives the star. As it orbits the star, its gravitational pull tugs the star just a little bit back and forth. We can measure that tug by looking at Doppler shift of absorption lines in the stellar spectrum. So we can figure out something about the mass of the planet, but we don't know its exact mass because we don't know how the orbit is tilted. On the other hand, if you want to get the radius, you've got to look at a star and just be lucky that a planet is going in front of the star and shadowing it, eclipsing it a little bit so that the light dims a little bit. And then you can figure out the fraction of the star's area that's covered by the planet and get its radius. If you have one of those planets and you do the radial velocity observations, then you also know what the tilt is, so you get the mass exactly. So if everything works out right, you can get the mass and the radius of the planet. This particular planet has a mass of about 6.5 times the Earth's mass and a radius of about 2.7 times the Earth's radius. So it's kind of big compared to Earth, but not Jupiter size. And its density, when you divide those numbers, is about 1.87 grams per cubic centimeter. So water has a density of 1, roughly, and rock has a density anywhere from 3 up to, depending if you have metal in it, it could be higher. Iron has density near 8 grams per cubic centimeter. So when you have a density like a little less than 2, this is telling you this is a water to rock ratio that's comparable to the ratio in Pluto or in Kuiper Belt objects, and its density is just about the same as Pluto. This looks like a planet that has a water-to-rock ratio near 1. And it's not the only one. As I said, though, you have to get very lucky. So out of these thousands of planets that have been discovered, there are this many planets that have masses that are less than 12 Earth masses, just to put an upper limit on it. So these are Neptune size or smaller, basically, a little smaller than Uranus and Neptune. We haven't yet found a planet where we know its density that's as low as 1 Earth mass, but we're getting there. But these are planets where we know the mass and the radius, and they are not too big. And I've listed them here, listed their densities, and made a little plot of mass of the planet and its density here. And what you find, this is where Earth would be, the green dot. And there are many planets that appear to be denser, or at least as dense, the red ones, or denser than the Earth. And the metal-rich ones, maybe, is what we're looking at when we see densities of 7, 8, 10 grams per cubic centimeter. But there's also a fraction of planets that are near 1 or 2 grams per cubic centimeter. And these are interpreted as water worlds. We still have to check to make sure that they don't seem to be so big because they have these big fluffy atmospheres blocking the light. But some work has been going on in the last year to follow up on some of these planets. And so it really looks like we're finding planets that are just low density because they're full of water. So why is that? And how is it that Earth got its water? And if you follow the path, Earth got its water because our protoplanetary disk had dust and ice in it. This was orbiting the sun, and then planets formed out of that. First, it formed smaller bodies like asteroids and comets. These combined together to form larger planets like Earth. And at any step along the way, you might just have lost water from these environments. I'll just say first, is it possible that you could have lost water during a collision? And it's possible that when 2 asteroids are combining, or Earth and a big thing like the thing that formed the moon, could you have lost water during that process? And there's some tentative evidence that something like this happened. When you look at the abundances of elements in the Earth and you compare them to meteorites, you find that some things that are chemically very volatile and easy to put into the gas phase are lost, and the more volatile they are, the more they are lost. And so there's this linear trend there. But there's some elements like chlorine, iodine, and bromine that are just way lower than that even. It has been interpreted tentatively that these are much lower than expected because these are the elements that today form salts and are only found basically in the Earth's oceans. And so you could lose these if you lost salt by losing an ocean, maybe during an impact. But other calculations that look at how much of the ocean you could lose and how much atmosphere you could lose and how much ocean you could lose based on the impact speeds from things hitting the Earth. They suggest you could lose all the atmosphere, but you have to be in this range. You couldn't lose more than 20% of the ocean, today's oceans. So, I don't know. It doesn't look like the Earth lost very much water, but that means it wasn't born with a lot of water. And why was that? Where did the Earth get its water? The official story has long been that it got it from comets. That it did not get it from comets because 2 things. Comets bring in too many other chemicals that we don't see on Earth, especially noble gases like argon. And if you look at the isotopes of hydrogen in the water in comets, they are very rich in deuterium, the heavy form of hydrogen. And we don't know of a way that you can get the Earth to lose deuterium relative to regular hydrogen. But this ratio of deuterium to regular hydrogen actually in meteorites from chondrites or from asteroids, that the value in those bodies matches what we see in the Earth. So the inference is that the Earth got its water from asteroids, basically, from the same building blocks that form the asteroids. And when you look at asteroids today, we have different types of asteroids. As a function of distance from the sun, close by ones, they're called S-type asteroids. They have a certain spectrum when we look at them. But then if you look at asteroids closer to 3 to 4 AU, they're more of this other type called C-type asteroids. And then there's other types further from that. S-type asteroids have been associated with ordinary chondrites, meteorites that don't have a lot of water, 0.1 weight % water. whereas C-type asteroids have been associated with carbonaceous chondrites, which have lots of clays and can contain up to 10% water by mass. If you were to bake them, they would release steam. So this seems to be what the building blocks of planets were. You had dry things inside of about 2.7 AU, that blue line, wet things beyond that. And if that were the case, you could understand where Earth got its water. These are simulations done by Sean Raymond where he imagines building blocks that are dry inside a certain radius and wet, blue and red denote water content outside that radius. And then he simulates how planetesimals bang together and form bigger planets. And by the end of the simulation, you're here, he's formed 5 planets in this solar system. And they all have some water, even though they're forming at regions like inside of 1 AU where the building blocks were all dry. Just the stochastic nature of how stuff gets banged around allows Earth to get some water. So that's actually good news. I guess Earth could get water even though it was dry. But actually, when you go through the numbers and you say, okay, in this simulation, I've got this planet. Where did it get its water and building block material? And here's the range. This blue line is where it's got its material. And so some tail of it is from regions that had abundant water in them, even though most of it is from dry things. Some of it is from wet things. But when you do the math, it turns out Earth should still have like 1% water, not 0.03% water. So that's a mystery. Why is it? The official story is that Earth got its water because some asteroids from beyond 2.7 AU were accreted during the Earth's formation, but still you'd expect more water. This official story doesn't explain everything. And anyway, why is it that asteroids inside 2.7 AU are dry and ones beyond that are wet? Why do we accept that fact when in fact we should expect asteroids even inside 1 AU to be wet? When you look at protoplanetary disks, and you ask what are the temperatures in protoplanetary disks, we find that they should be hot enough to vaporize ice inside some radius and cold enough for ice to condense outside some radius. So closer to the sun, hot, no ice. But where that line is, it's just commonly thought, why not 2.7 AU? But in fact, when you do the math, it should be at 0.8 AU. It should be inside the Earth's orbit. And so it's hard to understand why, if it was cold enough for ice to condense, why wasn't there a lot of ice in the inner solar system for Earth to accrete? I'm working on a model that I can't get into, but I'm explaining why the Earth is dry because there was no ice in the inner solar system because in an earlier stage it was kind of all sucked out. All the water vapor was sucked out by this process called external photoevaporation. If a solar system forms in a region like the Orion Nebula, as I've drawn here, then these are protoplanetary disks that are forming planets today. Here it is zoomed up. These little black things are the protoplanetary disks where planets are forming right now in this star-forming region. And you see this cocoon of gas around it. That's because these bright stars in the Orion Nebula are emitting so much UV that they are boiling off gas from the disks. And as part of this process, I argue, those solar systems will see their inner parts dried out. And if the Earth formed in such an environment, then it could have been that it was cold and yet it couldn't have condensed ice, and Earth is dry for that reason. All right, if that pans out, it's because of ultraviolet radiation. Only half of all stars actually form in such regions. Half of stars form without all of this ultraviolet radiation, and I think you're back to this question of why aren't they would ice condense in their regions? And I think roughly half of stars will have planets like Earth that are dry. Half of stars will have planets that are water-rich. So I think this might go a long way towards explaining plots like this, that you have roughly equal numbers of planets discovered so far that are water-rich versus dry like Earth. And that really motivates a lot of thinking. What about these planets? Are they good for life? Would you want to buy real estate there? Right now on Earth, we have this carbonate-silicate cycle. We have a lot of CO2 emitted from volcanoes, but that CO2 is dissolved in the oceans. And because of water-rock interactions, a lot of calcium ions are released from rock. These can combine with carbon dioxide or carbonic acid, and they form carbonates. And so most of the carbon dioxide that the Earth has spit out of volcanoes has actually been locked up in limestone, which is really good for our atmosphere. But on a planet like these, how would they work? You have volcanoes, Mount Everest to scale here, by the way. Volcanoes emit gas, and the gas might seep out if the ice is convecting. It could seep out into these oceans and collect in an atmosphere. But where is the water-rock interaction to produce these calcium ions that you need? If there's no calcium ions or other cations in the ocean to draw down the CO2, you could build up a lot of CO2 in the atmosphere. And it's been predicted that 20 bars, 20 atmospheric pressures of carbon dioxide could build up. And that greenhouse effect would run away to like 230 degrees Celsius would be the surface temperature, again, if you put Earth at 1 AU, but with this sort of ocean. And the pH of the ocean would be about 3.2, very acidic. And there'd be very few nutrients in this ocean. Is that good for life or not? And I don't know, but that's what we're trying to work on. So Earth-like planets with lots of water, they were speculated to exist. And now we're finding that they probably do exist. And it's a mystery. Why isn't the Earth such a water world? It should have been cold enough for ice to condense. We should have accreted a lot of ice during the Earth's formation. But we're working on understanding that. And it will tell us a lot about how other solar systems work and about the real estate. Maybe these are not good planets for life. That's an example of what we want to do in astrobiology. Assess whether these are good planets for life, how would life work on such planets, so that we can say, what are we looking for when we want to know if life exists there? And I just can't resist putting one last slide. If, let's say these water worlds do exist and they did have life, could we communicate with them? I've often thought that if water worlds are very common, this goes a long way to explaining the Fermi paradox. Fermi asked, where are they? Where are they? Why haven't we found them yet? They should be abundant. Even if you had dolphins with opposable thumbs, how would they make radio telescopes to communicate with us? But these are things we can imagine now because of discoveries like Kepler about water worlds. One example of things we're studying in astrobiology. Thanks.
Are there any questions?
Yeah, really briefly, the way this model works is it doesn't really heat up the disk because the central star is the main determinant of the temperatures. But what it does is it removes gas from the outer edge of the disk. And that removal of gas causes gas from the inside to flow outward much more than in a normal protoplanetary disk. So at an early stage, when disks are hot, you can have water kind of be sucked out. And then when it cools down, as disks do, and it's ready to condense ice, that water is no longer there.
And so basically causes it to migrate outward.
Yeah. Cool. And for Ariel, too, if there's questions, too.
I'm a freshman in the astrobiology program here at ASU, and when I tell people my major after they get done being confused, they like to joke, "Oh, I didn't know we found something." Do you guys get that a lot in the scientific community?
No, it's real. How do you even know what to look for, though, unless you start asking the questions? Yeah.
I'm also an astrobiologist studying here as a freshman. And I wanted to know because I've heard many stories of scientists actually working with like cells and stuff, like trying to not create life, but like shifting things. For example, phosphorus with arsenic to see if it works out. I wanted to know how far exactly are we with that and seeing how versatile life really is.
So our group has put a lot of effort. The arsenic thing is one of those efforts into trying to figure out what the range of what we call element stoichiometries are for biology and how different the element composition can be. How far you can push Earth like life. And the answer so far seems to be, not very much. We look, it's very hard as it turns out. You might be easy to go to. What we want to know is, for example, if you look at extreme organisms living in Yellowstone hot springs or something like that, what are they? What's their elemental makeup? How different is it from you or me, or some microbes in a non-extreme environment? And you might think that's easy to do, but it's really hard to actually get the data. And we spent years trying to get data in a way that's reliable. And there's a big error bar. But the extent that we get it, we don't see anything surprising. There are some unusual enzymes that use unusual metals, but the bulk elements, carbon, nitrogen, phosphorus, of course they're all necessary to do that, but the relative ratios of those elements to each other are don't seem to be dramatically different in microbes that live in extreme hot environments and really bizarre metabolisms of their organisms versus sort of typical microbes. So at least on Earth, life seems to be stoichiometry and doesn't mean there can't be before that.
In our search for exoplanets, are we only looking at solar systems with stars the size of our sun? And if not, do we change the capital zone?
Yeah, I'll answer that. So the easiest stars to measure the Doppler shift of absorption lines in their spectrum are ones like the sun. And it turns out that red dwarfs generally have more active atmospheres that smear out the signature that you're looking for. Nevertheless, there are a lot of red dwarf stars, many more than sun-like stars. And so you have almost an equal number that are close enough that you can make up for those factors. And so they're starting to look at those a lot more now, too. And both have zones around them where life, where water could exist on the surface, and therefore life might have an easy time. So they're both worth looking for in that respect.
So obviously we'll know we aren't alone, or it's their life, but how would we know we are alone?
It's very hard to prove a negative, right? All you do is search and search and search and things are getting frustrating. I mean, it's lost your science. I can't give you the right answer. You'll never be able to prove that we're statistically unlikely. You can admit balance.
All right, we have time for one or two more questions.
Hi, this is Kyle from University of Colorado. I find this field of research absolutely fascinating. I was wondering what are current satellites or telescopes, instruments out there that are contributing to this field of study, and what are instruments and telescopes that are coming out in the future that are contributing to this?
All right, that's all the time we have for today. Thank you very much.